Yay, implicit differentiation. Now, know that this is a very, very big deal. You want to understand this and pay attention at the very beginning of this and really understand, because often you are not going to be dealing with functions. Let me explain. I'm going to bring the textbook over to show you. You're going to need to take the derivative of things that aren't exactly functions where you can isolate the y with respect to x. And in fact, you might get some amazing curves out of them, but they are not nice functions where you can just easily go, oh, I'll take the derivative using all my rules. Oh, I'm not giving you the doubles curve. Ha 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 ha. Anyway, so know that that is what you are doing. Right now, you're only going to be working with variables x and y. Later, you're going to be working with a variety of variables, and you need to know the difference between an unknown constant and a variable. Now, I know the textbook is really bad about telling you when you have an unknown constant, but any test I give you and the AP test must tell you when you have an unknown constant. So let's say C represents an unknown constant. Represents. Then if I tell you to take the derivative of that constant times x squared, you just use the constant multiple rule. And you go bring the constant down, multiply by the derivative of x squared, 2x, voila, done. But if C is representing a variable, when it represents a variable, that means there's an entire set of numbers that you are going to go through and plug in and get different values out. So there's a big difference. An unknown constant means you just don't know what it is, but it is just a number. You just happen to not know it yet. So let's say I give you w times x squared. And I say that w represents a variable. In that case, I can't do what I just did up here. But how do I do it? Before I show you how to do it, I want to talk to you about what you already know and use that to help you. So I'm going to erase some of the work that I have here. If I can get my eraser working. There we go. And I'm going to start with something you are familiar with. Everyone, take the derivative of x squared times tangent x. You know how to do it. And you need to start with the product rule. So we have keep one function, multiply by the derivative of the other, and everyone the derivative of tangent is secant squared. Plus, then I take the derivative of the x squared and I keep the tangent. Now, what if you didn't know that tangent was the function? And I want to see if I can move this up. There we go. What if you were presented with this expression, take the derivative of x squared times y instead? What I want you to see is that this is the derivative of tangent x. this is tangent x itself. And as we go a little bit farther into some examples, I'm going to show you how you're actually just using the chain rule when the function gets more complicated than this. But I'm just starting off with something simple to get you to see that you're not doing anything new. It's just odd, so to speak. All right. So if you were asked to take the derivative of x squared y, you would need to look at it and go, all right, keep the first function, multiply by the derivative of y. Well, if I'm taking the derivative with respect to x, what is the derivative of y? It is just plain the derivative of y with respect to x, whatever it may be. Plus, then you would take the derivative of your x squared like normal, but the y would be kept as just keep it. And I just want you to see the side-by-side comparison of that. Now, I want to also point something out to you with your homework. It's asking you to find dy dx. The focus is the denominator. Anytime you have to do implicit differentiation basically means that you have to take the derivative and you have a variable that is not the variable you are differentiating with respect to involved. So the key is when it asks you to find, come on, here we go, dy dx. This is what is telling you who you need to take the derivative with respect to. And the dy dx itself will naturally come out within the process if you just go with respect to that bottom variable. So let's get an example going. I'm going to move this example up. Okay, take a look and read this. And also know it's coming from your textbook, so you can also look at your textbook later if you want to see more. For part A, it's asking me to find dy dx, and I've got an equation. So what I'm actually going to do is I'm going to do to one side what I do to the other side. Basically, I'm doing an operation on both sides of my equation, and that operation is differentiation with respect to x. So I am going to dx both sides of my equation and then set them equal to each other. All right, here we go. You know that you get to separately differentiate over addition. So we start off with x squared. What is the derivative of x squared with respect to x? And you go 2x, yes. Plus, now, listen carefully. Listen carefully. When I run into a variable that is not who I'm differentiating with respect to, make it a baby function. I need to chain rule this function the way that I would if this was tangent of x squared. So I actually start off with who's the mommy function. The mommy function is blah squared. The power rule says the derivative of blah squared is 2 blah. The chain rule says that I take the derivative and I give mommy her baby and I multiply by the derivative of that baby with respect to x. I didn't use any new derivative rules. All I'm doing is making a variable a baby instead of a nice little tidy expression that is more obvious how to go about taking its derivative. And in fact, I can't take the derivative of y. I just have to leave it as whatever dy dx happens to be and deal with it. But actually, that's what I was asked to find. On the other side of the equation, I take the derivative, and I want to give you just a moment. So what are we taking the derivative of with dy dx? Basically, it's just whatever y happens to represent, and you don't know what it's representing. And that's what's going to feel awkward. And it might help if you just maybe temporarily say, what if y is tangent x? So you can temporarily go, all right, what if this was x squared plus tangent x squared? How would I take the derivative? And for some of you, that will help you to see why you get here, what you get. Because on this, you would go derivative is 2x plus 2 times blah times the derivative of blah. And what I'm saying right there is it. 2 times blah, give mommy her baby, times the derivative of that baby. And realize that if tangent x is actually a replacement for whoever y is, that's exactly what I'm doing. I just happen to not necessarily. The thing is, if I were to isolate y, it could be a nightmare. And that's what I don't want to do. I don't want to isolate y for the functions I'm dealing with here. And there are going to be situations where there's nothing you can do to isolate your variable. Now, I want to bring up a question that period 1 asked at this moment, because it always shows up. And that is, why didn't I chain rule when I did the derivative of x squared? So let's look at the chain rule if I'm dealing with x squared. If I want, I can see this as blah squared. So if I take the derivative of blah squared, the chain rule says that I do 2 blah times the derivative of that blah. Now, x is the blah, so 2 blah times the derivative of that blah with respect to x. And hopefully you see that this turns into a ratio that's just times 1. Some people feel more comfortable calling every single variable a baby function. And then just when they run into something like dx over dx, they change it to a 1. And that works perfectly fine. You just don't have to do it for the specific variable that you are with respect to taking the derivative. And as you look at this, you can see why that one variable you don't have to do it for. So what you're really seeing with implicit differentiation is just a bigger picture. And that bigger picture allows you to understand the value of the notation dy dx as opposed to using y prime. Now, A lot of you don't want to write dy dx every time you have to take the derivative. It is okay. You are allowed to just put y prime down. Completely allowed. When I do it, I'm always going to use this notation because I feel it is actually very, very valuable and important to see what's going on. Using this is more, I get it. You don't want to write a ton of stuff down. So anyway, I'm going to keep moving forward. And I need to take the derivative of 25. I didn't do that yet. Are you ready? Derivative of 25 is? Now, did anyone think for any moment 25? Be honest. It's very likely to happen to you at some point while you're doing these problems. I don't know why it happens. I would love to study the psychology of why is it when you are doing implicit differentiation specifically that people mess up when they're taking the derivative of a constant when it is by itself. I can't tell you why it happens, but I am warning you that you will be surprised when it does happen. And you look at the answer and you go, wait a minute, why did I get the wrong answer? And then you finally figure out that you literally wrote down that the derivative of 25 was 25. It will happen to you. I'll be surprised if it doesn't. Okay. So we have not done what the problem asked. The problem asked us to find dy dx. I'm going to erase this bit down here and look at the fact that this is my equation. And we call this a differential equation because it has a derivative in it. But I now need to treat dy dx as a variable and isolate it. So to isolate it, I'm going to subtract 2x, and then I'm going to divide by 2y. And so I end up getting the answer as dy dx is negative x divided by y. Now, part B, find an equation of the tangent. It should be worded tangent line, but that's what they mean. Find an equation of the tangent line to the circle. And before, when we had nice functions, I only had to tell you an x coordinate. There was an automatic singleton y coordinate that came out of it. But with these guys, you have to be told the full point. So equation of tangent line, y minus the y coordinate. Okay, move, there we go. The y coordinate is 4 equals, I'll find the slope in a moment, x minus the x coordinate. And then for finding the slope, I'm just going to plug in x equals 3, y equals 4. And let me make sure you know about this notation. If I want to explain that I'm taking the dy dx as a function and plugging in the point 3, 4, then I draw a line that goes down below it and put that point there on the bottom right of the line. Then you can say negative 4/3, and voila. And that's it. That's your tangent line. And now I'm going to move on to example 2 so that we don't run out of time. Because we could look at the picture and it would be fun. But if you want, I think the textbook shows it, but you can also go to Desmos and type that in. You know that Desmos will draw for you. You can just write a bunch of x's and y's with an equal sign and it will draw that, even if it's not a function. All right, here we go. Next problem. This one's going to get a little bit harder. obviously. Otherwise, we wouldn't do another problem. So we want to find y prime. Know that that means find dy dx. I don't like the y prime notation because it isn't specific enough to clarify to you that it's actually dy dx. On a test, you need to be told much more specifically. Here we go. We are going to ddx both sides of the equation. With the addition sign, I get to separately take the derivative. So derivative of x cubed with respect to x, 3x squared, plus. I'm not taking the derivative with respect to y. I need to then treat y as a baby. And I have blah cubed. The derivative of blah cubed is power rule 3 blah squared. And then according to the chain rule, I give mommy her baby, and I multiply by the derivative of that baby with respect to the x variable. On the other side of the equation, I want to warn you, the AP test loves to give you problems like this on the right side. In fact, I can pretty much guarantee you they're going to give that to you. And a lot of people, the reason they love to give it is because of how badly people will mess this up. So pay attention. I can group the 6 with the x and say I've got one function that is 6x multiplied by another. I'm just going to say, quote, function, relation, really. So I'm multiplying a 6x and a y. What rule do I need to use? The product rule. The common mistake is people just don't product rule it. They just take the derivative straight across the board. So be very careful. Now, here we go. According to the product rule, I am going to keep one, multiply by the derivative of the other. What is the derivative of the other in this case? What is the derivative of y when I'm with respect to x differentiating? Just dy dx. Or if you prefer, you can write y prime. Plus, and then I switch who I differentiate and who I keep. So if I differentiate 6x with respect to x, I get 6. For the second function, if I just keep it, then I just plain keep a y. So while I am differentiating with respect to x, I'm getting some dy dx's. I'm also keeping some y's at the same time. And that's normal. Know that with showing work, this needs to be clear. You need to very clearly show your derivative taking rule by rule. On the AP test, you don't have to show algebra steps. If you can do algebra in your head, you can write down dy dx equals and call it a day. But not everyone is able to do it in their head correctly. So I'm going to talk you through the algebra of it. And for the sake of visual, I'm going to erase what's up on top here because it's bugging me. It's melting into the problem. There. Now it's prettier, and I can look at just that. Okay. Look for your dy dx's because if you're going to find dy dx, that means you're going to isolate it like as if it were just a variable. And that's why another reason why people like to write it as y prime. What you want to see is this dy dx is multiplied by 3y squared. This dy dx is multiplied by a 6x. You have to combine those two. And you can combine them by subtracting one of them over to the other one's side. So here we go. I've got my 3y squared times dy dx, and I'm going to subtract over 6x times dy dx. Now, I can lead this with 3x squared plus, but I really don't want to have to write more algebra than I need to. The quickest way to get through this problem is to have all the terms that are going to be factoring a dy dx out of them on one side of the equation, and all the terms that don't have a dy dx factor on the other side. So that means that I have the 6y already on the right, and subtract the 3x squared over to join it. And now notice that the left side has a common factor. So undistribute that multiplication by dy dx, and then you are really, really close to your answer. Do you see what one step you have left and you're going to have the answer? What's that one step? What is the one thing you need to do? It could just one word. Divide, yes. Divide and you're done. You may want to simplify after that, but you have isolated dy dx. You can call it a day at that point on you have found dy dx. Sometimes the AP test will, in a free response problem, tell you the dy dx and ask you to show that that is the dy dx for the expression or the equation we began with. In that case, you have to simplify it down to what they have. So very likely they're going to have top and bottom divided by 3. So I'm going to go divide by 3, divide by 3, divide by 3, divide by 3. By the way, I say that every time because if I don't, I will fail to divide by 3. You guys probably do that in your head when you're taking a test. It's very valuable to do that. Now, know that you might see the answer written another way. All I did was switch the order of subtraction on the numerator and denominator, which is equivalent to multiplying the top and the bottom by -1. They are exactly the same thing. And whether your answer winds up looking like this or this is just a matter of which side, the left side or the right side, did you choose to put dy dx. That is, so when you look at the answer, know that maybe the answer looks like this, your answer looks like that. It's the same thing. Be able to just recognize that. Now, let's see what else we needed to do. That was part A. Part B, find the tangent. Oh, this is such a special curve. It's called the Filium of Descartes. And we want to find the tangent line at the point 3, 3. that means that I'm going to need to determine what is the slope at the point 3, 3. And then just take either equation to plug in. Excuse me. And what do I get when I plug in the 3, 3? -1. Now that I know my slope and my xy coordinate, I write the equation of the tangent line. And I've got this ready to show you in Desmos. If I can find where I put Desmos. Yay, there it is. Is that cool? So the folium of Descartes and the tangent line at that specific point. And that's a really important point, as you can see. As far as quadrant 1 is concerned, that is like the point that is farthest distance-wise from the origin. All right. Now, back to work. The next problem, at what point in the first quadrant is the tangent line horizontal? Now, all I've got to go with is I know that I need to set the slope equal to 0, right? Tangent line is horizontal when the slope is equal to 0. And really, that just means when the numerator is 0 and the denominator is not 0. Now, how on earth are we supposed to get anything with that equation alone? You're not. We have another equation that involves x and y. Where is the other equation that involves x and y? That has to be a truth for what we are dealing with. The original equation. Whatever xy pair makes the derivative equal to 0, it also has to plug into this x and y and get a true validity out of it. So that means I can use this. I have x cubed plus y cubed. Let me write that down. Equals 6xy. By bringing those together, I actually have a system of equations, two equations, two variables. Can I solve this? Yes. Now, one thing I want to say is when you're solving a system of equations where it's not just a couple of linear functions, you may find that you try one way and it doesn't work. You try another way, it doesn't work. And then finally you look at the answer and go, oh my gosh, how did I not see that that was going to work? When it comes to solving systems of equations like this, if you're in the middle of a test and you have time on that test, it could take you a while. And maybe it should have been obvious to you, but take your time. Now, what techniques do I have available in solving a system of equations? Some of you remember the words. What techniques do I have? Substitution. That's like the big one. Elimination. Now, you're trying to figure out what maybe is between the two equations. Is there a variable easy to solve and isolate? That's often going to help you if you ask yourself that question. In this first equation, nobody's easy to isolate there. In the second equation, I can isolate x squared, but I don't know that I really want to deal with a square root. Isolating y, let's go with that. So I isolate my y, and that gives me y equals, excuse me, x squared divided by 2. And now let's go back and substitute that into all the y's of the other equation. My other equation is x cubed plus y cubed equals 6x times y. And then keep going. Yes. Because then I read above. Perhaps I should double check with my algebra and go slowly. Add 2y to both sides. It is positive. Double check me. You guys see it as positive? Okay. Yeah. Easy to do. Whenever you skip algebra steps, you run the risk of making the mistake. And you see, I even had to double check because I don't trust myself when I skip algebra steps. All right, so let's see what I've got. I have x cubed plus, now I need to cube my numerator and my denominator. So I have x to the 2 times 3 and 2 cubed. And then I can do a little bit of cancellation there to make my life better. And I have 3x cubed. And then I can subtract over, and I now have x to the 6th over 8 minus 2x cubed equal to 0. Now, we are in quadrant 1. If I am in quadrant 1, my x not only is just greater than 0, but let me emphasize that it cannot be 0 itself. If my variable is not allowed to equal 0, I can divide both sides of the equation by it, and I don't risk losing solutions that I should have gotten. But know that if you divide by a variable, you have to be positive that it can never be equal to 0 for that particular problem. So I'm going to divide by my x cubed. Wait, hold on. Divide by x cubed means subtract. I can do this. Exponent rules. You could also get this if you factored an x cubed out. So I add 2 and then divide or multiply by 8. I can do this. 2 times 8, 16. So I am getting that the cube root of 16 is the x coordinate. This might be a grab a calculator moment. Can someone tell me the decimal number, 3 digits after the decimal point? Cube root of 16. Someone put that in a calculator. And once I know x to find y, go back to one of the simplest equations that you have available. This is going to be probably the nicest one. Okay, so 2.52, give me one more digit after that decimal point. The AP test expects 3 digits after a decimal point, so I am going to really push that on you. Right. On the AP exam, you either write 2.520. It is acceptable if you write 2.519 because you are allowed to either truncate, which means just take off the terms past it, or round up if rounding up is okay. And with that, then plug it in over here. And what do I get for y in decimals? 3.176. All right. Now I'm going to type that point in to Desmos. So luckily I can see chat on the screen. I've got x coordinate 2.5198, y coordinate 3.176. And that said that was where I have a slope of 0. I'm going to take this off because that's really in the way. Does that look like there's a pretty good chance that's a 0 slope? Yeah. All right, so that was fun. That means we are done with example 2. The next is example 3, and then we will get to example 4. Oh dear, I'm looking at the time, and that's not fantastic. Like, really not fantastic. For the purpose of, I'm going to keep this video going when you leave for lunch. If you want to stay, you can stay. I'm going to move to example 4 because I need to talk to you about that one. I really need both, but let me make sure I get this one across. And again, when it hits 10:50, you can feel free to leave or stay. I will post this video and I will keep the video going. Okay. You need to find y double prime. So that means you have to first find y prime. And y prime specifically means dy dx. So I'm taking the derivative with respect to x of both sides of my equation. Using the sum rule, I can take the derivative separately over the addition, and that gives me 4x cubed when I differentiate with respect to the x variable, plus, and then I need to take the derivative of blah cubed, which would be, according to the power rule, 4 blah cubed, according to the chain rule, give mommy her baby and multiply by the derivative of that baby with respect to x. And then keep going, equals, and then the derivative of 16 is 0. When I isolate dy dx, I am going to get a negative 4x cubed divided by a positive or x cubed, or y cubed. I end up getting this. Now, if I want to find y double prime, I take the second derivative. I take the derivative again, but of this. By the way, you can take the derivative a second time in this format, but people tend to be more accurate in their derivative taking if they isolate dy dx first. So here we go. I am going to take the derivative with respect to x of both sides of my equation. The d dx of dy dx is the second derivative of y with respect to x. On the other side of the equation, I need to use the quotient rule. So I'm going to let the negative go with the numerator. So I've got low d high minus high d low. Now when I go for the d low, I have to realize that I'm taking the derivative with respect to x. Y is a baby function. So derivative of blah cubed is 3 blah squared. And then give mommy her baby and multiply by the derivative of that baby with respect to the x variable. We're in the middle of quotient rule, so square the bottom, and away we go. But we're not going because you're expected to find the second derivative in terms of just the variables x and y. And I'm going to warn you that your textbook loves to do a ridiculous amount of simplification. You might be surprised how much. And I'll leave it there and let it be your enjoyment when you get there. So I am going to need to substitute into this dy dx what dy dx happens to be. So I'm going to rewrite this. I have negative 3x squared y cubed plus 3x cubed y squared times dy dx, negative x cubed over y cubed. Now at this point on an AP exam, you would be considered done with you have found the second derivative of y with respect to x. However, you're probably going to need to simplify it with whatever technique you're using. But that's what you needed to know about taking the second derivative implicitly. And if it's okay with you, I'm going to leave any extra simplification for you to look at on your own. And I'm going to move over to, it is now 10:50, by the way. If you need to leave for lunch, I will continue to video and post that video. And so here I go. I have two sides of the equation. If I'm going to find y prime, that actually is referring to dy dx. If I'm going to find dy dx, I have to differentiate with respect to the x variable. I am going to then d dx both sides of this equation. Here we go. I have a parentheses right after my sign. That means baby function. Using the chain rule, I start off with the mommy function is sine of blah, derivative of sine of blah is cosine of blah. Chain rule says, give mommy her baby, multiply by derivative of baby. Just to clarify, this is what I'm now doing. So derivative of x plus y. With respect to the x variable, I can separately differentiate over the addition. Derivative of x is 1, and then the derivative of y with respect to x is dy dx. On the other side of the equation, I need to use a product rule. So I've got keep the first function, multiply by the derivative of cosine x, plus now I'm going to take the derivative of the y squared and keep the cosine x. But as I take the derivative of the y squared, I need to see the chain rule. So the mommy function is blah squared. Derivative using power rule is 2 blah. Chain rule says give mommy her baby and multiply by the derivative of that baby with respect to x. At this point, I have done all the derivative taking, but I still need to isolate dy dx. And maybe you see the algebra of it, maybe you don't. But let me clarify for you something that you really, really need to see. You need to see that this must distribute over this addition. Before you can even begin to isolate dy dx, you have got to do that distribution. So multiplying by the 1, I get cosine of x plus y. Plus the cosine of x plus y times dy dx. On the other side of the equal sign, I have a clear dy dx lonesome multiplied by other stuff. So that's ready to be dealt with. I'm going to rewrite this to negative y squared times sine x plus 2y times cosine x times dy dx. And if it's okay with you, I'm going to do the algebra in a quick one-step way. If this causes you to make mistakes, don't do it this quickly. So let's say I decide that I'm going to move this over to the right. That means that the left side will have the cosine of x plus y. And I need to add this y squared times sine x. That doesn't have dy dx as a factor. On the other side of the equal sign, I have my 2y times cosine x. Oh yeah, I was going to do this in one swoop, wasn't I? Actually, I've already started, so. Minus the cosine of x plus y times dy dx. Once I distribute dy dx out of all of this, I will have what is not highlighted in a parentheses, and I will be dividing it to the other side. So I have cosine of x plus y squared times sine x divided by 2y cosine x minus cosine of x plus y. And that is it. Now, do some of you feel like you could use some more examples? Do you think people could use more examples? Okay. I could keep going with the video, and these were extra problems for in case I have time, but I think people could use it. So I'm going to go ahead and go over these. These are problems that I'm going to not end up assigning for homework at any point. So I will go over them. If you want to stick around, keep in mind this is your lunch time. I will keep recording. Okay. All right. Continuing on. For number 8, I need to, in order to find dy dx, those are the directions, by the way, I need to ddx both sides of the equation. For the left side, I have 2x cubed plus x squared y minus xy cubed. On the right side, I have just plain old 2. So taking the derivative with respect to x over the addition subtraction signs, I get to differentiate separately. With respect to x, the derivative of 2x cubed will give me 6x squared plus, and then, oh goody, look, I get to do a product rule. Ah. So product ruling, and I'm going to make sure to keep this kind of color-coded for you. So I'm going to highlight the derivative in yellow that comes from this piece once I get it out there. So product rule, keep one of them, multiply by the derivative of the other one with respect to x. Plus, this time take the derivative of x squared with respect to x and keep the y. So all of this is taking the derivative of the x squared times y piece. I've got my minus sign ready, and I'm going to highlight this one in blue. Oh, look at that. It's a product rule again. Ha ha ha. So I keep one, I multiply by the derivative of the other. As I go through the derivative of y cubed itself, I need to see that it's really a baby function inside of a black cubed. So power rule on the mommy function. Derivative of black cubed is 3 blah squared. Chain rule says give mommy her baby and multiply by the derivative of that baby with respect to the x variable. Now let's be careful. I really should be putting a parentheses when I see a subtraction sign. I am in the middle of a product rule. Plus, now I'm going to take the derivative of x with respect to x, and I'm going to keep the y cubed. And then on the other side of the equation, I have the derivative of 2. It's a constant, so its derivative is 0. At this point, I've done all the differentiation. Now it's an algebra issue. So I'm going to rewrite. I have 6x squared plus x squared times dy dx plus 2xy. And I'm distributing my negative sign. I have 3xy squared times dy dx minus y cubed. It can help to highlight your dy dx's. I just realized that maybe I want to use a different color of highlighter. And I also remembered that I was going to do this in case you need it to see that the derivative of the entire xy cubed is all of this. And you can always pause right now and take a good look at it. In the meantime, I'm going to move on with the algebra. So I'm going to highlight my dy dx's. Then I'm going to look at what is the rest of their term. Who are they multiplying with? So this dy dx is multiplying with an x squared, and then I've got plus or minus signs around that. This dy dx is multiplying by 3xy squared, and then I've got subtraction and or addition to the sides of what I just underlined. I need to isolate them on one side of the equation, get everything that is a term that does not have dy dx as a factor on the other side. So that means I'm going to keep this x squared times dy dx minus 3xy squared times dy dx. And I'm going to add, subtract everything over to the right. So I'm going to add y cubed. I'm going to subtract 2xy. And I'm going to subtract 6x squared. Then I look at my dy dx's and realize that they are a common factor on the left side of that equation. So I factor that common factor out, or undistribute the multiplication of dy dx. And once you get to this step, all that's left is to divide. So dy dx is equal to this numerator divided by that. Okay, now I'm going to move on to problem number 10 and talk you through that one. And I'm going to move this out of the way. Come on. Okay, number 10. I'm now working on number 10. I need to ddx both sides in order to find dy dx, because again, the instructions are find dy dx. I've got a very big giant left side. I've got a nice big giant right side as well. And it's derivative time. Yay! Over this addition sign, I differentiate separately. I look at y to the fifth. That does not have the variable I'm differentiating with respect to, which is x. So I'm going to have to chain rule this. And I need to look at y as a baby function. The mommy function is blah to the fifth power. The derivative of blah to the fifth power is 5 blah to the fourth power, using the power rule. Going back to the fact that we have a baby, the chain rule says give mommy her baby and multiply by the derivative of that baby with respect to the x variable. Now I'm going over to the other side of this addition. And now, oh look, oh, we get to do a product rule. Who's excited? Huh? All right, here we go. I'm going to keep the x squared and multiply by the derivative of y cubed. And since I'm going to have to do a bit there, I'm going to remind myself that I'm doing product rule so I don't accidentally take the derivative of y cubed and forget that I have a plus after that. And I will be taking the derivative of x squared. With respect to x, the derivative of x squared will be 2x times keep the second function. So now I am taking the derivative with respect to x of y cubed to put here. treat y as a baby function if it is not the variable you are differentiating with respect to. See that the mommy function is blah cubed. That makes the derivative 3 blah squared. Give mommy her baby and multiply by the derivative of that baby with respect to the x variable. At this point, you have taken the derivative, and now it's algebra from here. I'm going to erase this down here. And then I'm going to isolate. To prepare for isolating dy dx, I'm going to highlight them, and then I'm going to look at who is multiplying with the dy dx. So who has dy dx as a factor? You know what I just realized? I have not finished the derivative. I just finished the left side. Who thinks that's funny? Okay, probably not you. All right, I am taking the derivative of the right side. So derivative of 1 with respect to x, 0. Don't really need to write it, but I will just to emphasize. Now I have two things that are multiplying. So I need to product rule. Here we go, product rule. I'm going to keep the y. I'm going to multiply by the derivative of e to the x squared. Continuing with product rule, plus I'm going to be keeping the e to the x squared and multiplying by the derivative of just y itself. And the derivative of just y itself is dy dx. Coming back to needing to take the derivative of e to the x squared. You need to see that what you have is e to the blah. In other words, you have a chain rule. The baby just got circled, it's x squared. The mommy function is e to the power of blah, where blah is just the variable of the function. So the derivative of e to the blah is e to the blah. And now I've got give mommy her baby, multiply by the derivative of that baby with respect to x. The derivative of x squared with respect to x is 2x. My product rule is done. Now I've actually taken the entire derivative, and I've got to actually shrink that down to see the entire line. And I'm going to finish what I was in the middle of doing with highlighting the dy dx's. I'm going to erase this ddx that's in the way right now. I just wrote that down to say, hey, right here, I need to take the derivative of somebody while I finished writing out the product rule so that I didn't accidentally forget that I was in the middle of a product rule. All right, now I need everybody who has dy dx as a factor to be on one side of the equation and move everybody else to the other side. I have 5y to the fourth times dy dx plus 3x squared y squared times dy dx. And then minus e to the x squared times dy dx. And then who I don't have underlined in red is who needs to be on the right side. This one is already there. So rewriting this, I'm going to write it as 2x times y times e to the x squared times, not times. And then I have this term, 2xy cubed, and I need to subtract that over to the right. I'm going to re-highlight dy dx, all of them, and then see that it's a common factor. So I am undistributing the multiplication by dy dx and leaving 5y to the fourth plus 3x squared y squared minus e to the x squared. And then the last step that I must do to at least isolate dy dx is divide. And then I'm done. I can choose to simplify that if I want. I don't have to. I do want to point out that you might do this work. You might do work on a problem similar to this and go look at the answer and find out that the answer looks like this. Realize those are identical. All I did was I multiplied the top and the bottom by -1. And the reason that the answer might be written this way instead of the way that you have there is because when you make the choice of, do I want dy dx to be on the left side, or do I want to move everybody else to the left side and have dy dx on the right side, you will get the exact opposite signs of everything. So either way, you have a correct answer. And then I can move on to the next problem. Do you need to go out? Give me a moment while I let my dog out. There you go, baby. All right. I'm going to do one more problem with you. Number 12. I'm supposed to find dy dx. So that means that I'm going to ddx both sides. On the left, I take the derivative with respect to x. Over the addition, I take the derivative separately. Derivative of 1 is 0. I'm not going to bother writing it. Derivative of x is 1. So that entire left side is just 1. The right side is a beauty. Notice that there's a parentheses following those 3 letters, not a variable. So I need to do a chain rule, and I'm circling the baby. I need to take the derivative of sine of blah. So remembering my derivative formulas, derivative of sine of bleh is cosine of bleh. After I've taken the derivative of sine of bleh, I remember that I am in the middle of a chain rule. So I need to give mommy her baby and multiply by the derivative of that baby with respect to x. And if it helps, you can write down that at this moment, I now need to take the derivative of xy squared. That is the focus of all of this, and it must multiply to what I have so far. The sine and the cosine have been taken care of. Do not go back to them. Your only focus now is just this. So here we go. Ooh, I've got a product rule. Yay! So I'm going to keep the first, multiply by the derivative of the second, plus keep the second and multiply by the derivative of the first. Now I'm going to do what's easiest first. So derivative with respect to x of the first, which is x, is just a 1. But then when I go to the derivative of the second, I've got to realize I'm taking the derivative with respect to x. Y is not an x. I need to see this as bleh squared, not y squared or x squared, but bleh squared. Power rule says derivative is 2 times bleh. The chain rule says give mommy her baby and multiply by the derivative of that baby with respect to x. Now that is the derivative. I'm going to rewrite it so it's nice and clean to take a look at what we need to do next. The thing you need to very importantly realize is if you look at dy dx and where it is, you should see that you have to first distribute the multiplication of cosine of xy squared over this addition. You're not going to be able to isolate dy dx. Actually, you could divide by cosine of xy squared to the other side and then go about your algebra. How about we do it that way? Since we can. So I'm dividing the cosine of xy squared, and that is equal to what was in the parentheses. Then to isolate dy dx as if it were a variable, I need to first subtract the y squared. And then I need to divide by 2xy. And maybe this is why it would have been better to distribute the multiplication of cosine of xy squared over this addition, because now I have to deal with a fraction and a fraction. But that does not make this incorrect. If I'm not concerned about simplification, this is a correct answer. If I am concerned with simplification, then I am going to take this single-termed denominator, no addition, subtraction, and distribute the division over the 2 terms of that numerator. And again, I'm distributing division. That means it's going to show up in the denominator multiplying to the cosine of xy squared. I don't have to write the little times symbol, but just to emphasize. And then minus y squared over 2xy. Know that the answer is most likely going to write this as a single fraction. And I can see that the factor I don't have is the cosine of xy squared. So I'm going to multiply numerator and denominator by the cosine of xy squared. And now I have my common denominator. And subtract the numerators. And this is the answer I would have gotten possibly more quickly if I had dealt with the distribution right in this spot right here. If I had done distribute the multiplication of the cosine of xy squared over this addition, I probably would have gotten there faster. But being correct is the most important thing in math. Although when you're testing, sometimes being faster can be the balance between the two has a relative maximum. Oh, we'll get there soon. All right. Then that is it. I hope you enjoyed the examples, and I will see you online.